Hello everyone, this is week 11 of structure analysis taught by Professor Amit Shah. I am Trisha Chakraborty, one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. As always, we start with a brief recap of the previous 10 weeks. We The course is basically divided into two phases. In phase 1, we covered analysis of determinate structures. Uh, in week 1, we cover types of internal forces. There is bending moment, shear force, axial force, and torsional moment. In week 1, we covered types of internal forces, common classification of elements like beam, frames, trusses, and boundary conditions like fixed hinge support, roller support, internal hinge, etc. And we looked at structural indeterminacy and bending moment and shear force diagram. In week 2, we focused on trusses in particular, how real world 3D trusses are idealized as 2D trusses that can be analyzed easily, the stability of trusses, and solving the member forces in a truss using method of sections and method of joints. In week 3, we looked at the other kind of response that is of a structure that we want to study. There are two kinds of responses. One is the force and the stress response. That is what we solve when we solve the member forces of a truss, from which we can get the stresses in the members by dividing by the cross sectional area. And the other kind of response are displacement or strain response. So for that, we looked at the principle of virtual work, which has a lot of application in civil engineering and in structure analysis in particular, and that gives rise to the unit load method to determine displacement in truss. In week 4, we looked at the deflection response of beams. So there are several methods. The three major methods we looked at are the elastic curve equation method, the moment area method, and the conjugate beam method, which we looked in week 5. And basically, moment area method and conjugate beam method are both based on the elastic curve equation method, but they are, I mean, simplified presentation of the elastic curve method, where we don't actually have to solve the differential equation. So it is a shortcut. Both moment area and conjugate beam methods are shortcuts, and they all three of the methods will give the exact same result. In week 6, we looked at influence line diagram, which is a little different from the other parts of the determinate analysis. Influence line diagrams are useful when the loading pattern is not fixed. Like in all real world structures, the live load component, it can move, right? I mean, the furniture, the cars, trucks, everything can move. The position can change. So influence line diagrams helps with judging that kind of response. The Mueller-Breslau principle gives us the influence line diagram qualitatively, and we also looked at how to obtain them quantitatively. Now, from week 7 onwards, we moved on to the second phase, that is the analysis of indeterminate structure. As I said before, all real world structures are indeterminate, because the more degrees of indeterminacy you have, the safer the structure is. So we cannot rely on a just determinate structure where even if one support fails, the entire structure will collapse. So the number of extra support reactions, so the number of extra members we have inside a truss or something, are the degrees of indeterminacy, and they make a structure safer. So we reviewed degree of structure indeterminacy. We were got introduced to force and displacement methods, Maxwell-Betty's reciprocal theorem, and method of consistent deformation, which is a force method. Then we did up to this was the force method. Then for the displacement methods, we need kinematic indeterminacy and the displacement methods. Week 7, week 8, and week 9 were the method of consistent deformations applied to beams, trusses, and frames. And from week 10, 11, and 12 are the three major displacement methods: the slope deflection method that we looked at last week, the moment distribution method, which we are going to look at today, and in the final week we will look at the stiffness matrix method. The slope deflection and the moment distribution methods are the ones which are generally used. You will be asked to solve using these two in exams or in subjective exams, and in objective exams as well. Stiffness matrix method is too complicated to carry out by hand, because even a 3 by 3 matrix is difficult to invert. So as we will see the next week, it is like stiffness matrix method is mostly a computer. It can be easily computerized, so that is why we are introduced to that in this course. But for solving by hand, the slope deflection and moment distribution methods are the ones we really use. So structural indeterminacy, we just briefly look at it, that we have looked at before. Structures that cannot be analyzed using statics or equations of equilibrium only are called indeterminate structures. They require other material properties, and the degree of indeterminacy is the number of unknown reactions minus the number of equations of equilibrium. External indeterminacy is the total number of independent support reactions, total number of available equations of static equilibrium, and internal indeterminacy is the total number of internal reactions minus the available equations of equilibrium. And degree of structural indeterminacy, the total one, is the sum of the external and internal indeterminacy. Generally, we have formulas to find out all three, but it is easier to find out external indeterminacy and the total degree of structural indeterminacy. So from that, we can find out the degree of internal indeterminacy as well. Here are some examples we have looked at before. This is a cantilever beam. This is a determinate structure because in the 2D plane there are three equations of equilibrium, and the fixed support also provides exactly three support reactions, delta Fx, Fy, and Mz. So 3 minus 3 is 0, so it is a determinate structure, or the degree of indeterminacy is 0. This is a propped cantilever. This is a fixed support, and on this corner there is a roller support, so it gives an additional reaction in the vertical direction. So there are four unknown reactions and three equations available. So this is 1 degree indeterminate. This is a frame. Again, a 2D in a 2D frame, the fixed support will again provide three support reactions. So there are total six support reactions, three at A and three at D, and the total number of equations available is three. So 6 minus 3. So this structure is indeterminate to the third degree, and this is a frame with two hinge supports. Hinge supports do not provide any moment reaction. They provide reactions in the x direction and in the y direction. So there are four unknown forces and three equations. So this is 1 degree indeterminate. You briefly look at the two approaches that we follow to solve indeterminate structures. The force methods and the displacement methods. So force method is also called compatibility or flexibility methods. Redundant here, as we have seen in the method of consistent deformation several times, that the redundant forces are chosen as unknowns, and the additional equations are obtained by considering compatibility conditions, that is the geometric conditions imposed to ensure the continuity of structures. There are several methods: the method of consistent deformation, unit load method, strain energy method, method of minimum potential energy, and flexibility matrix method. But method of consistent deformation is the one that is looked at in detail in this course. These others may be looked at in future advanced courses. Then there is a displacement approach, that is also called the equilibrium or the stiffness method. Basically, flexibility and stiffness are inverses of each other. I mean, for example, in a spring has a spring constant called K that we call the stiffness, right? So 1 by K is the flexibility of that spring. So you can say flexibility and stiffness are complements of each other. In displacement methods, the displacement of joints are taken as unknowns, and equilibrium equations are expressed in terms of these displacement and internal loads. These equations are solved to give the actual joint displacement from which the redundant forces can be calculated. And in both these approaches, once we have the redundant reaction forces or the redundant member forces, we can treat it as a determinate structure, because suppose a structure has four support reactions, and using any method we manage to find out one of the reactions, then we can treat, for example here, in this structure, this is indeterminate. Suppose we find out this support reaction RC using a method of considered deformation or slope deflection method. Then we can just treat the RC as an applied load on a cantilever beam, because the structure reaction forces and applied loads are equivalent. They are all just applied loads to the structure basically. So we will apply RC as an applied load, and we will solve the cantilever beam. We can solve everything, right? We can solve bending moment shear force diagram, we can solve the displacement profile, everything, once we have a determinate structure. So basically our goal is to solve all the redundant forces so that we end up with a determinate structure that we can fully solve. So these equations, and there are three methods. There is a slope deflection, moment distribution, and stiffness matrix method, all three of which are important, mainly the first two. These are the differences between the two methods summarized. In force method, unknowns are taken as internal member forces or reactions. In displacement method, unknowns are taken as joint displacements. In force method, to find the unknowns, we write compatibility conditions, and the number of equations required is the degree of static indeterminacy, that is the number of unknown forces. And to find the unknowns in displacement method, joint equilibrium conditions are written. So the number of equations required is the degree of kinematic indeterminacy. We looked at kinematic indeterminacy last week. So if this degree of static indeterminacy is ds and degree of kinematic indeterminacy is dk, we Initially, if you are given an indeterminate structure, we should calculate these two values, because if ds is less than dk, we would prefer to go with the force method, because then we will have lesser number of equations to solve. And if ds is greater than dk, we will choose a displacement method. This is kinematic indeterminacy. Degree of kinematic indeterminacy refers to the total number of independent available degrees of freedom at all joints. So basically, here, for example, in a 2D truss, we know that a 2D truss joint, there are only two kinds of displacement it can have, right? In the x direction and y direction. So these are also called the degrees of freedom. So every node in a 2D truss has 2 degrees of freedom, delta x and delta y. In a 3D truss, it's the same thing. There are only translational degrees of freedom, but there is also one in the z direction, because it is in the 3D space. So there are 3 degrees of freedom: delta x, delta y, delta z. Now in a 2D frame joint, rigid joint is also called, it is also basically a frame joint. So we know that what in a frame, every joint is free to move in the x direction, the y direction. It is also free to rotate in that in the plane, I mean in the z direction. In the plane it is present, so its sense will be in the z direction. So we call it theta z. So delta x, delta y, and theta z are the 3 degrees of freedom. So it is important to note that in 3D truss and 2D frame joints, both have 3 degrees of freedom, but they are different kinds. So in truss there is only translational degrees of freedom, while in frame there is translational and rotational degrees of freedom. So in a 3D frame, there are all 6 degrees of freedom possible, because beyond 3D we cannot go. In 3D we know there can be maximum 3 translational displacement and 3 rotations. One about the x-axis, one about the y-axis, one about the z-axis. So in a 3D frame, all 6 degrees of freedom are available. So the degree of kinematic indeterminacy is simply obtained by knowing the number of possible degrees of freedom. From that we have to subtract the support reactions, because if, for example, here, if there is a fixed support, I mean, this is a beam element. This was supposed to have 2 degrees, 3 degrees of freedom. But if you fix it, we are basically fixing all 3 degrees of freedom at A. So that is why we have to subtract the support reaction from the number of degrees of freedom. So the formula is simple. For 2D truss, it's the decay is 2j minus RE. This is 3j minus RE. This is also 3j minus RE, and rigid jointed space frame will be 6j minus RE. And there is something special, like some special cases, like if some members are actually rigid, that this delta x is not available, then for each such member you have to reduce that, I mean you have to reduce the x degree of freedom. So for 2D jointed rigid frame, dk is 3j minus re minus m double dash, where m dash dash is the number of actually rigid members. And for 3D jointed frames, 6j minus re remains the same. You also have to subtract m double dash. So, determine degree of kinematic indeterminacy for the given cantilever. If the beam is actually flexible, which is what we normally expect, so there are two joints, A and B. Every support or every free point is a joint here, not the load. If there was a load here, there would not be a joint there. The joints are basically the support and the end points basically. So there are two joints. So there are total 6 degrees of freedom possibly available before you implement the boundary condition. If you just have a beam AB, then there can be 6 degrees of freedom, three here and three at A and three at B. Beam acts same as frame. So delta x, delta y, and theta z, and there are three support reactions, right? In the fixed support, there fx, fy, and mz. So all 3 degrees of freedom at A are constant. So total number of degrees of freedom is 6 minus 3 equal to 3. Now if the beam is actually rigid, you have to subtract an additional degree of freedom, that m dash dash, it is one member, so we have to subtract m dash dash, and we end up with dk equal to 2. Determine degree of kinematic indeterminacy when member AB is actually rigid. So what do we have? We have 6, 3 into j is 6, and RE, there are both at hinge support, so there is fx, fy, fx, fy, so there are 4 support reactions. So we get dk equal to 2. And now see, even if AB, whether AB is actually rigid or not here does not matter, because in this case, since the x direction displacement is restrained at both A and B, it cannot, it cannot deform in the x direction anyway. So that is already incorporated here. So the decay remains 2 here. Here, if it is not actually rigid, then B can move. So the delta x is actually free for B. That is why we had to subtract it. Here we don't have to subtract 1 anymore. This is another special case. In rigid jointed frames, some of the joints may be hybrid. That means internal hinge basically. So if some joints are hybrid, then additional degree of freedom will be available. So decay has to increase. So if m dash is the number of members meeting at a hybrid joint, that is at an internal hinge, for 2D, for 2D RR is sigma m dash minus 1. I mean sigma is for each internal hinge. If there are two internal hinges, then you have to add for m dash minus 1 for both of them. And in the 3D space, this RR value becomes sigma 3 into m dash minus 1. We have looked at something similar like this in static indeterminacy as well. Some examples will make it clear. This is a normal, this is a continuous beam. So there is a fixed support. See here there are three joints, because since there is a support point here, this you have to count as a joint. So 1, 2, 3, and 3 J is 3. So the formula is 3J minus RE, and there is no nothing called axially rigid here, or there is no internal hinge. So we use the regular formula, 3 into 3 minus RE. How many reactions are there? Two at one at this roller, one at this roller, and three here. So there are five reactions. So decay is 4. Here there is an internal hinge. And how many members are meeting at the internal hinge? Two members, right? AB and BC. So the RR here will be m dash minus 1, that is 2 minus 1, 1. So applying the formula, there are four joints, A, B, C, D are all joints, because they are in frames and trusses, it's actually easier to identify the joints. In beams, you just have to see that all support points and all free points has to be nodes. So decay is 3 into 4 minus RE. RE is this fixed support gives 3 reactions. The hinge support gives 2 reactions. So RE is 5 and RR is 1. So with this formula we get 8. This is a beam with an internal hinge, and internal hinge also has to count as a joint. Whatever be the configuration, an internal hinge is always a joint. So there are three joints. There are five support reactions: three from fixed support, two from hinge support, and this RR is again two members are meeting, BA and BC. So RR is 1. Applying this formula, you get decay equal to 5. 3 into 3 minus 5 plus 1. And there are no actually rigid members, so m dash dash is 0. This is a frame. This is a really complicated frame, and this support reaction is interesting. Maybe you may not have seen this before. See, in an ordinary roller support, we draw two wheels. So if it's a roller with two wheels, the way we draw a triangle with two wheels, then it means that the x direction movement is free, and rotation about the z plane is also free. A roller, ordinary roller, only restrains the vertical displacement, right? Assuming it is resting on the vertical plane. Basically, a roller restrains movement perpendicular to the surface it is lying on. But this is a different kind of roller, the one with three wheels. It actually restrains the moment as well. It does not allow rotation, so it gives a moment reaction as well. So the number of reactions here, from fixed support we get 3, from hinge we get 2, fx and fy, and from this roller we also get 2, which is fy and mz. It is free to movement in the x direction. So there are 7 reactions. How many joints are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. And they are saying that beams are actually inextensible. If the beam, see in this if you see buildings around you, buildings are held up by beams and columns. So the vertical members are columns and the horizontal members are beams. So if they say beams are actually inextensible, this means 1, 2, 3, 4. The four horizontal members are actually rigid. So m dash dash is 4. I mean these vertical ones are the columns. Okay. So decay is, and there is RR is 0 here because there is no internal hinge. So 3 into 9 minus 7 minus 4. 16 is the degree of kinematic indeterminacy. And here they show, basically they are showing the degree of kinematic indeterminacy. See, for this point it is free to move in the x direction. This point is free to rotate. This point is not free to do anything. This This is a similar kind of question. Here there are 1, 2, 3, 4, 5, 6, 7, 8, and 10. Since there is one thing here, you have to count this as a joint. Number of reactions is 3 plus 2 plus 1. This is an ordinary roller. So 6. And there is no RR or M dash dash. So simply 3 into 10 minus 6, 24. Now we move on. Now that, I mean, kinematic indeterminacy is needed to get into the displacement methods. And what um, kinematic indeterminacy. If we get the degree of kinematic indeterminacy less than the degree of static indeterminacy, we will try to apply our displacement methods like slope deflection as we looked at last week, and this time we will look at moment distribution method. This method is used to analyze statically indeterminate beams and rigid frames. Here, every joint of the structure is to be analyzed. Uh, they are assumed to be fixed in moment distribution method. Every joint in the structure are assumed to be fixed. Fixed means the all three degrees of freedom are restrained. Then each fixed joint is released one by one, and the fixed end moments which are not in equilibrium at the time of release are transferred to nearby members until equilibrium is attained. So we do this in the form of a table. This is of course sounds confusing right now, but a few examples will make it clear. This is what is meant by stiffness. Firstly we need to know what stiffness is. Displacement methods are also called stiffness methods. So stiffness for a member at a joint is the moment or force required to produce unit rotation or displacement at that joint. Stiffness at a joint depends upon end conditions and properties of cross sections. Just for a moment forget about structure analysis and think of the spring we learned in class 11, 12, or even before. How is the spring constant defined? In a spring that is fixed at one end and we put a mass in the another end, or a force F, we say that F equal to kx, right? So k is F by x. That means that if you put x equal to 1, that is if you want to deform it by a unit length, if you put a unit deformation in the spring, what is the force developed in the spring? That is F, right? If you put x, that is k, because if you put x equal to 1, F equal to k. So basically stiffness, the concept of stiffness is force per unit displacement or moment per unit rotation. So now we put that in the context of structure analysis, especially in the context of beams. So we considered a prop cantilever. Here, AB is a prop cantilever, A is fixed and B is hinged. So for the prop cantilever, if an anticlockwise moment is applied at the end B, if you apply moment like this, then rotation at B is given by ml by 4 EI. This value you have to find out by other methods. I mean, this value they are taking for granted. So m by theta. So you get. So basically here you have to find out this theta. You, if you want the stiffness, the rotational stiffness at this point, you have to apply a moment, and you have to find out the theta. That you can find out by any method. That we can find out by the moment area method, or uh, since it's an indeterminate structure, you have to first apply slope deflection or something, and then apply moment area method maybe to find out theta b. So you have to find theta b, which will obviously come in terms of the moment applied, and m by theta b will be the stiffness. So m by theta b, or if you put theta b equal to unity, then the moment will be 4 ei by l. So the rotational stiffness of b is 4 ei by l, and we write as aba since the force is since this is the member we are considering, we write B before because the moment and the slope we are considering at B. Now we consider simply supported beam AB. Again, we will do the same thing. We will apply a moment at M and we will calculate the theta B. This theta B we will see as ML by 3 EI. So KBA is 3 EI by L. Therefore, it is said that the stiffness of a member when farther end is fixed is given by 4 EI by L, and stiffness of a member when farther end is hinged is given by 3 EI by L. And stiffness of a member when farther end is free is 0. Of course, if the other end is free, there will be no stiffness generated. So these two values, 4 EI by L and 3 EI by L, are important in the moment distribution context. Now here, uh, we consider as a continuous beam. KBA is 0. See, what we have to do for the moment distribution method is we have to find out the stiffness at every joint with respect to its left side and right side. So we need KBA, that is 0 because A is fixed. Now we need KCB is 3 EI by LY, because if you stand at C and look at B, you find a hinge support, right? So it doesn't matter what is the condition of C, it doesn't matter. So the support condition of B only matters. So KCB is 3I by L, and KCD, if you look at D you find a fixed support, so KCD is 4I by L. Similarly in this joint, suppose you want to find out all the stiffness at O with respect to all four. See, if you want KOOC, it will be 0, right? Because C is a fixed support. If you look at KOD, it will be 3 EI by L because D is hinged, and KOA and KOB will all both be 4 EI by L. look at an example. A steel frame is shown. If joint O of the frame is rigid, the rotational stiffness of the frame at point O is given by. We have to simply add all the stiffness since it is rigid. So what will we do? This side KOD gives no contribution. KOD is 0. KOB is 3 EI by L. KOC is 4 EI by L, and KOA is 4 EI by L. So we add all these three and we get 4 plus 3 plus 4 is 11 EI by L. It is the net rigidity or the stiffness at O. Then there is a concept called carryover factor. See, this stiffness, carryover factors, distribution factors, all these are the ingredients we need to solve using moment distribution method. So carryover factor is defined as the ratio of the moment at the fixed far end to the moment at the rotating near end. Carryover factor is here if this moment, I mean, here at B, moment M is applied, and at the fixed end MA is applied, then the carryover factor will be MA by M. So for this beam, this prop cantilever, at at the x distance from B, if you see, there will be a reaction here RB. So RB into x plus M will be M, and this is basically the applying the elastic curve equation method. You can apply any method, but you can find out the MA. Integrating, we will get an expression of y, and if you solve, we will get that this whole y expression, this you will get. So from that you can solve ma. If you solve, basically this derivation is not that important because you just have to remember this. Ma comes out to be m by 2. So in a fixed, if this end is fixed, then if you apply moment m here, and a moment of m by 2 gets transferred in the same sense. Like here you are applying an anticlockwise moment m, then at the fixed end you get an anticlockwise moment of m by 2. This is what you have to remember. This derivation is not very important. So the carryover factor is half. So see, the magnitude of bending moment at the fixed support of the beam is equal to. So we just, this is at the free end you have a force P. At this point you know that at this point the moment will be Pa by 2. Sorry, PA, because moment P is applied at a distance A from this point. So PA, so you can treat this, if you forget the part BC, you can transfer a moment of PA at B, and if you apply a moment PA at B, there will be a moment will be generated this in the same sense, in the anticlockwise sense, PA by 2. So the fixed end moment here will be PA by 2. What is the carryover factor from A to V while using moment distribution for analyzing this beam? This is a beam of varying cross section. So here we have to see that what moment is being applied here and what moment is carried over here. We use the area moment theorem, but I mean, I think this is a bit too complicated to go into right now, because in the questions we will encounter, we will only undergo continue same cross section and simpler configurations. So we look at the distribution concept of distribution theorem. If a moment which is applied to a structural joint to produce rotation without translation gets distributed to the connecting members at the joint in the proportion of the stiffness or relative stiffness. So what did we do earlier? We took a joint O and we saw that the stiffness in each direction. In A, B, C, D, here there are five. So A, B, C, D, E, all will have a stiffness. Like this side will be have this O B will be 4 E2 I2 by L2. This A, this hinge OC will be 3 E3 I3 by L3. It will depend on the Young's modulus, the moment of inertia, and the length. All these three will be provided, and you just have to see whether the other end is a fixed support or a hinge support. Based on that, you will give 4 or 3. So that is the ratio. So there are 5. So in this 5, A, B, C, D, E, these are the stiffnesses. 4 EI, E1 I1 by L1. B will be have 4 E2 I2 by L2. C, D, and E will have 3 EI by L. So this will be the ratio in which the moment will be divided. So 3 by 4 I by L is called the relative stiffness of a member whose further end is hinged, and I by L is relative stiffness of a member whose further end is fixed. This is just a fact. It may not be applied directly. And the distribution factor of a member at the joint is the ratio of the stiffness of the member to the total stiffness of all members meeting at that point. So see, if you add all these five quantities, if you add and you divide all the quantities by that summation, you will get five ratios adding up to which you will get 1. So this distribution factor is stiffness of member by total stiffness of joint. So summation of distribution factor of the members at a joint will of course be 1. Here we consider this rigid joint. Stiffness at O is 4 EI1 by L1 because it is fixed. Stiffness at B is 4 EI2 by L2. At C and D are 3 3. So we add the 4. If we add the 4, we will get this delta K, and the distribution factor for OA will be K1 by delta K. At OB will be K2 by delta K, and similarly. So the applied moment M is distributed in all the members in proportion of their stiffness. So at O, if you have a moment A, then you will divide that into M1, M2, M3, M4 in the four members in that ratio. And the sense has to remain the same. It is an anticlockwise. See, all the moments here are anticlockwise. This M1 is anticlockwise, M2 is anticlockwise, M3 is anticlockwise, M4 is anticlockwise. And according to that, you know that the fixed and the moment transferred here will be M1 by 2, because that we saw in a fixed end then it will be M1 by 2. At this fixed end it will be M2 by 2, and C and D will have no moments because of course hinge supports do not give moment reaction. That you have to keep in mind. So what we will do at for each joint, we have to find out the total stiffness, then we have to find out the distribution factors of all the members meeting at that joint, and we will find out the carryover moments at the fixed ones. If there are fixed end this side, that side, however many fixed ends are there, that many number of fixed end moments we will get carryover moments, and the hinged ones will have no moment. Now these are some fixed end moments that we can remember. For example, for a fixed beam, if you apply a midpoint load P, then MAB and M bar BA will be PL by 8, PL by 8. This is more important for slope deflection method, which we did look at last class. If you apply a force P at a distance A from this end and B from that end, the moments will be minus PAB square by L square and PA square B by L square minus plus. The left side is always considered minus and the right side is plus, because for in case of downward loading, you will get anti-clockwise moment in the left side and clockwise moment in the right side, and the sign convention is anti-clockwise moment is negative, clockwise moment is positive. Now these are, I mean, very specified cases. These, you, even if you don't remember the first three, you should remember a point load at the midpoint, the point load at a general point, and this UDL on the entire span of the beam. Then the fixed moments are WL square by 12. Minus and plus you can put accordingly. And these are some values that you will find in any standard textbook. You may remember these, but the first three you should remember. Now we move on to the procedure of analysis of moment distribution method. Find fixed end moment for each member, considering each end to be fixed. Every joint you have to consider fixed. Sign convention for fixed end moment: clockwise moment is positive, anti-clockwise moment is negative, as I said. Then for each joint, we have to see how many members are meeting, and we have to find out the stiffnesses of all the members, and from that we will find out the distribution factors for all members meeting at a joint. Each joint is considered rigid. What does rigid mean? Rigid mean that it itself is not translating in any direction. Then we will find the unbalanced moment at each joint, and we will distribute the balancing moment at each joint according to the distribution factor. Then we will carry over the moment to the further ends if the further ends are fixed. If the further ends are hinged, don't have to look at it. If there nothing will be carried over. Then we will find final end moments at the ends when all the joints are balanced, and then we can draw the BMD, SFD, whatever, as discussed. Sign convention as we saw this. Okay, so let's look at an example. For the beam shown, we have to analyze using moment area method. So fixed end, first what will we do? We will look at the, or both the ends of the beam will always be considered fixed. So this is fixed, this is fixed. And the fixed end moment we have to, there is a 50 kilonewton here. Okay, sorry. All the supports are basically fixed. So A is fixed, B is also fixed, C is also fixed. So first we look at the AB span. If we look at AB, there is a midpoint at the center. What was the formula? PL by 8. So L is 8. So MAB bar is minus PL minus 50 into 8 by 8. So minus 50 kilonewton meter. And MBA bar will be plus 50 kilonewton meter. And now if we look at the span BC, we need MBC bar and NCB bar. If you just see the part BC, there is a uniformly distributed load, and what was the formula? It was WL square by 12. So L here is 4, W is 25. So MBC bar is minus 25 into 4 square by 12, and MCB bar is 25 into 4 square by 12. So this is minus 33 and plus 33. Now the distribution factor, there is only one joint at which we have to look at distribution factors, at B. We need distribution factor BA and BC. So this side is also hinged, this side is also hinged. E and I is constant, they will say, but the lengths are different. So this part BA has length 8 meter and BC has length 4 meter. So remember, BA stiffness is 4EI by L, that is 4EI by 8, and BC has 4EI by 4. So the total stiffness is 12EI by 8, and we can divide it in the ratio. So this is 1 by 3 and this is 2 by 3. So 1 by 3 and 2 by 3 are the distribution factors. And now we draw this table. See, in this table you have to start with fixed end moments. You will draw A, B, C. You will write down the distribution factors one third, two third. If there are more than one member, more than two members, you will look at that later. Then first you have to start with the fixed end moments. First you forget there is any loading, first you forget there is anything, just put the fixed end moments, minus 50 plus 50 on this side, minus 33 by 33 on this side, and 33 by 33. Now this moment is not balanced. Our aim eventually is to put this moment equal to 0. I mean, the moment at B should add up to 0 from BA and BC, because this is a roller support, and a roller support does not give any support moment. So what is the unbalanced moment here? 50 minus 33 by 3, that is calculating 50 minus 33 by 33, 16.67. So there is a plus 16.67 moment unbalanced here. So we have to put minus 16.67 moment to balance it. And in what ratio will we put these moments? Here we will transfer one third of that unbalanced moment. Here we will transfer two third. So 16 into 67 into 2 by 3 is 16 into 67 into 2 by 3 is 11.11. So here we will transfer minus 11.11, and here we will transfer the rest, that is minus 5.56. And carryover moment at C, since both of these are fixed supports, we have to carry over half the moment. So 5.56 by 2 we carry here, and 11.11 by 2 we carry here. Now we add these. Now see, we add this, all these columns we add. So 50 and 2.77 we get minus 52.78. This adding we get 44.44. Adding this we get minus 44.44. So they have been balanced, because that was what we did, right? We took the balance moment and we got a positive unbalanced moment, so we gave an negative unbalanced moment of equal magnitude, and you add this 33.33 minus this, and you get this. So at joint B, the resultant moment here was 16.66, which was unbalanced. So balancing moment of minus 16.67 was applied at B in order to make the net moment at the joint 0. By the distribution theorem, balancing moment gets distributed in the proportions of the DF. So we have got the Ferdinand A and B are fixed, so we got the carryover moments. So now what do we have? We have the carryover moments. So we have moments at all the ends. At A we have, at A, at B is 0 we know, and at C we know 27.775. All these values we have. So we can simply draw the bending moment diagram, and this is for the moments generated in the structure. And apart from that, you also have to draw the BMD for the applied loads. Just forget about all the fixed moments, just treat them as simply supported spans. We will treat, once we have the fixed moment, the bending moment diagram will be a superimposition of the moments we have found out and the given loading, where we will treat the span AB and BC as simply supported. So if AB is simply supported, we know that the bending moment diagram will look a triangle like this. And if BC is simply supported with UDL, it will look like this, where the peak is WL square by 8. You should probably do remember that value by now. So the bending moment diagram will be a superimposition of this and this and this. And I look at the signs as well. Negative means anti-clockwise, so you will draw anti-clockwise, and since anti-clockwise here is hogging moment, this is uniformly negative. The sign conventions don't confuse. I mean, since it is plus here, don't put here as plus. Okay, the entire thing is negative, because this sign that we get from the table is anti-clockwise clockwise corresponding to. If you get minus, it is anti-clockwise moment. If it is plus, it is clockwise moment. Then once you are drawing the bending moment diagram, you move on to the sagging hogging sign convention. So here we see that all the moments are hogging, so we, as per our sign convention, we draw it as negative. And since these moments are sagging, these are positive. So you are superimposing this. We do not know the entire exact nature, because this is a straight line with triangles superimposed by a parabola, but you can draw it in this way. You look at another example. One, two, three, four. Here we have to take four. We have to take three spans: A, B, B, C, and C, D. And there are two joints we have to work with: B and C. Okay. So let us start the way we started. Fixed end moments. For MAB, we saw WL square by 8 is a fixed end moment. So minus 53.33 and 53.33. MBC and MBC and MCB, we use those formulas because a point load P at a distance A from left end, B from right end. So here A is 4 meter, B is 2 meter. So applying the formula, we get the two moments, and here the fixed moment is 0 because this is a sorry, at C MCD the fixed moment is minus 50 into 2 because this load is applied and multiplied by the lever arm. So now we find out the distribution factors at B and at C. A and D, the absolute ends, we don't find out the distribution factors there. So at BA and BC, if you look, BA has stiffness 4 EI by this length, and BC has stiffness 3 EI by this length, 4 plus 2. So you get the ratio as again a 2/3 and 1/3. And if you look at C, distribution factor of CB will be 3 EI by 6. Sorry, 4 EI by. Okay, this should be 3 I by 6 because this is a hinge support. But anyway, it doesn't matter because this end is free. So the distribution factor of CD is 0. So the entire distribution, the entire moment has to be transferred to this point B. At D, there can be no moment transfer. So we draw up this table as A, B, C, D. In B, we write this will be 0.67 and 0.33, and at C, 1 and 0 correspondingly, and we write the fixed end moments. At D, there is no fixed end moment. So here there is unbalanced force of 53 minus 133 minus 35.56 that we divide in 2/3 1/3 ratio as minus because this was a plus unbalanced moment. We write here. Here we see the unbalanced moment was negative, so we get a positive moment to balance, and the entire thing we write here. Entire thing we write on this side because this is 0, so the entire ratio here is 1. Then we transfer it to the fixed end moments. This side we transfer, this side we don't transfer, and here also we transfer in this side. Then now see, here it doesn't end in one step. Here this force is, if you add this up, this is still not balanced completely. So this 14.45 is unbalanced, so minus 14.45 you again divide into 2/3 1/3 ratio, but this here you don't have to. Here it has been balanced, so here you don't have to write. Then again this part you transfer here, and now if you add up, see, we will have to keep adding up at each point to see if they are being balanced. Here you see that this part and this part has been balanced. This is plus 100, this is minus 100. So C, at B and C we cannot have any moment because these are hinge support. Hinge supports do not give moment reaction, and at this point we get an anti-clockwise moment reaction, and at the D it will be 0. At D we will not transfer anything towards D, of course, because D is a free end, and similarly from B also we do not transfer anything towards C because the fixed end is on this side. And this is how we end up with the 5 fixed end moments. Now while drawing the bending moment diagram, we will draw the fixed end moments. This will be the joining by straight lines, and for this span you will have a parabolic by BMD. For this part you will have a triangle, this part you will also have a straight line triangle. So this is how you will superimpose and get the BMD. This is the last example we are looking at. So uh, okay, so the fixed end moments at A, B and BC are the two spans we are going to look at. Fixed end moment at MAB bar is, this is applied at the midpoint, so PL by 8 will be minus PL by 8, and MBA bar will be plus PL by 8. And MBC, this is a new loading condition that basically there wasn't there in the table. But remember it, if a moment is applied at any point in the span of a beam, fixed beam, then the fixed end moments will be plus m naught by 4 plus m naught by 4. Both will be plus because this moment is plus. If this moment was anti-clockwise, it will be minus. So we get plus 10 kilonewton meter at B, M, MCB bar and BC bar are both plus 10 kilonewton. And we have to look at the stiffness ratio at B because B is the only joint we are concerned about. So if you look at BA, this is 3 EI into one. See, here the moment of inertia I is different, so don't forget to implement that. So it is 3e into 1.5 I by the length is 3 meter. and here it is 4 because this is fixed in 4 ei by again 3 meter. So that this the total stiffness. You can find out the distribution factors as 0.53 and 0.47. We start by writing the FEM. FEM is fixed end moment. So at A there is minus 9. On A side B there is plus 9, and on C side there is plus 10, and here there is plus 10. So this is 19 is the total unbalanced moment. At B there can be no net moment. So minus 19 we distribute in the ratio of 0.53 and 0.47 and get this. And see here C can have moment because it is a fixed end, so we are not concerned about this part, but this is also a hinge support. A is a hinge support, so this minus 9 also you have to balance out, because in the final configuration A has to have net moment equal to 0. So we give plus 9, and that we simply carry over as half. See, when you're considering AB, you are seeing B as a fixed end, so you are just transferring half there. Now here the total unbalanced moment is this, the summation of these three. So this you transfer as this, in the ratio minus, then again this part you transfer as half, 2.115 by 2 you transfer here, and then if you add these you will see that the final moment here at A is 0, at B it adds up to 0, and at C it's something non-zero. So you can draw the fixed end moment diagram: 0, 1.05 and 4.478, and you can also draw the many moment diagrams for this part. This part, if you take a simply supported beam, you will get a triangle, this kind of triangle, and for here you will get just a simple platform moment of m naught, and superimposing the three you can get BMD. Now if you are asked for the shear force diagram, you can find it out, because now that you have all the moments, the only unknowns you have are these vertical reactions, RA, RB, RC, and that you can solve using, I mean, you can take the spans, you can take each of the span as a simply supported beam, and a simply supported beam you can solve, because even if there are moments on the two ends, you know the moments. So you can simply solve, and while you are solving AB and BC spans, you have to take this, okay, you have to take this 1.045. Though the net moment at B is 0, when you are solving for that individual span, you have to take the 1.045, and then you have to solve for RA and RB1, like we did in slope deflection method. And then for the BC span, you will again put this minus moment, anti-clockwise moment, and you will solve RB1 and RC. So then you will have all the reaction forces, and you have the applied load. So we can just, now that you have RA, RB, and RC, you can draw the shear force diagram. There will be jumps at A, B, C, and at this point, and in the moment diagram there will be a jump at this point because there's a concentrated moment applied here. So these were some simple examples of moment distribution method. I don't think more complicated questions will be asked, because uh, there will be time constraint in exams. So slope deflection and moment distribution are the ones that you can expect questions on. Next week, in the last week, we will look at the stiffness matrix method. So is there any question? Okay, then I will end the meeting. We will meet again next week with the further stiffness matrix method.